All right, students, I got a request for a solution from the hard book here, the University of Physics, and it's number 87. And I was just looking at it, and I can see why. This is a doozy of a problem right here for P1. Now, P2 is pretty straightforward, but let's read this. It says, a total charge Q is distributed uniformly along a thin, straight rod of length L. So here's the rod of length L. What is the electric field at point P1 and at point P2? Well, let me actually do P2 first, and maybe even say, maybe I won't even do that. I went ahead and I printed it up, but in my supplemental lecture, P2 is actually the same as number 83 that I did. And here's the URL to it. YouTube, and then these crazy numbers. So I thought you can look that one up if you want. But like I said, it's problem number 83. So let me not do that one again. That one, like I said, is pretty straightforward. Because in that video, I did 83 and number 84. And 84 is a little bit like P1, except it is easier because it has a semicircle of charge. So you're always the same distance away. This one is harder because you have a changing angle as well as a changing distance. And so I will say that when I assigned this, I didn't realize how challenging this one's going to be. So if you've got the strength to hang on for a few more minutes, let's do it together. But it is a doozy of a problem and beyond the scope of this class. So that's a mistake on my part. I should have never assigned this one here. So just know that this is a hard one, and you don't really need to do it, and it wouldn't be anything this complicated on the test. But as long as I put it on there, and a couple of you are asking, and so I'm going to assume some of you would have the strength to watch this video out. So I'm going to give it a try here. And I think it's probably best you go back and watch my 83 and 84 first. Excuse me, because like I said, 83 is this one where the electric field we add up or we do an integration and they're all in the same direction. But 84, the field keeps changing the direction but always has the same strength. And then this one is where it gets hard. And so let me maybe throw some color in here. If you think of a little chunk of charge dq somewhere on this rod, it would make an electric field something like this. And let me call it dE. But the key to this problem, or one of many keys, just like this one, is to recognize there's a symmetric twin. And if we kind of divide it in half, we will see that for every charge on the right, there's a matching charge on the left. That's what I mean by the symmetric twin. And the one on the left would make a field that looked kind of at this angle to the right, and the one at the right, the charge at the right, would make it over to the left. And because of that, the x components of these two would cancel off. And so if you imagine doing that for every little chunk of charge on here, there would always be a symmetric twin that would cancel off the x component. And so what that means is the electric field in the x direction, which if you went through a lot of work, you would get 0. And so, again, hopefully you did look at 84. That was kind of my argument here with the half circle, that you would have a symmetric twin. And so we can save ourselves a lot of math because we don't have to do half the problem. We already got the x component 0. Now, the y component, well, that's not so simple. And so as you look at the symmetric twins, they each have a upward or a y component, whereas the horizontal components are in opposite direction for their symmetric twin. So again, that's why I said the x component is going to come out to be 0. But what I will do then is say, let's just add up this half of the rod. Let's go from this 0 point to L over 2. And whatever number we get, and so I'll say the integral of the y component as we go from 0 to L over 2, and then we'll just double it because we get exactly the same from its symmetric twin. So that's kind of the argument. Like I said, if you see this argument, they're equal and opposite, so you get 0, so you don't have to do half the work. That's one component already done. This one, it's not 0, it's double what would be for half of it, so we've got to actually do a lot of work to do this half. But at least we'll have to do half the rod, not the whole rod, and double it. So maybe that makes it a little bit easier. All right, keep going on here. To get the y component, I'm kind of looking at this picture again, so here it is. And I'll angle this back to where the charge is. And maybe I'll even just write on here, call this angle theta. But if this is the vector, I would say it is the magnitude of the vector you get from this little chunk of charge. And then if you call that theta, then it would be times cosine theta. And so that's the connection between the y component and the magnitude. You magnitude and then cosine of theta gives you the y component. Now, then here's where our Coulomb's law comes into play. We could say, well, how do you calculate the electric field? And the equation we've been using in class is this, but that's for charge Q. We're talking about some microscopic piece of charge, so I will label it as dq. That'll be r squared. And then let me not forget the cosine theta. Okay. So again, we're doing some hard stuff here, and we haven't even gotten into the math yet. Although the math's going to be pretty hard too. So good, I hope you're still hanging with me here, but I'll just put a little parenthesis around here. So this is the magnitude of the electric field from this little chunk of charge, and then this cosine theta gives me the vertical component, and if I do half the rod, then I just have to double it. So those are the three pieces here. Okay, maybe I'll leave the 2 and the Coulomb's constant alone. Why don't we take a look at the charge, a little chunk of charge, and that has to do with the density. And again, I'll just say hopefully you did take some time to look at what I did in 83, and for that matter 84. And we called lambda the charge density, and you can do that by saying, well, let's take the whole charge on this rod and divide it by its whole length, or let's take a little chunk of charge and divide it by its little chunk of length. And so the analogy I keep saying is you can do the whole candy bar divided by the whole length of the candy bar to get the density of the chocolate, or you can break off one little square and say, okay, well, what is the length of that one little square? And I mean the mass of that, say, one little square, and divided by the length of that one little square. That ratio is going to be the same because it's uniformly, that's the key word there, it's uniformly distributed. Okay, so I'll come back to this, but for right now, let me just use the right-hand side of this. So I'm going to replace dq with lambda dx, and I still have my r squared and my cosine theta. Okay, and then the uniform, or the fact that it says uniformly distributed means that's a constant, and I can pull that in front of the integral. All right. So like I said, if you were able to hang with me that far, you're doing well. That is a bunch of, I would say, applications of reading math more than doing math. And, you know, what do these things all mean? I mean, just knowing to do an integral is kind of trying to understand what did we really learn in our calculus that, you know, this integral. In fact, that's why we even use a s for sum, and we then elongate it to make it an integral, because that's what it means. Of course, now we've got an interesting dilemma, because if you think about now actually doing this integral, and we're going to add up these chunks of charges, you would start here and go to 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 here. And so we would add up along the x-axis. And so my dx makes sense that I'm adding along the x-axis. But see, what's interesting is the angle would be changing. And so this angle up here would actually be the same as this angle. And as we started with this little chunk of charge, say right here, the angle's 0, but it kept getting bigger and bigger and bigger and bigger and bigger and bigger. So that changes, but also r changes. R is the distance away, and so this would be the r, and it would keep getting further and further, or bigger and bigger, as we moved kind of away from that point. So that changes, and that changes as that changes. And so we need to get this into one variable, one or the other. And you might recognize this in your calculus class as one of the harder ones, because it has some trig stuff in it. And you might remember the trig identities. And so it's because of that, it's probably best to change this to all thetas. And so I have cosine theta, but let's figure out mathematically how x is related to theta and how r is related to theta. Okay? And then we can do a little switch. So coming back at this picture and maybe calling this theta, you could see that then this distance here would be x, and this vertical distance, I've kind of covered it up, but your author calls it a over 2, and then this piece is the hypotenuse r. So if we kind of focus maybe on r, and how r is related to theta, let's avoid, though, using an x. Because my first reaction is a Pythagorean theorem that says, okay, well, this x squared plus a over 2 squared would equal r squared. And that would change my r into an x, but that doesn't really solve my problem because the x changes. And so I got rid of one thing that changes and replaced it with another thing that changed. So what this is telling me is I should probably look at cosine theta for a second. The reason that is important is because it does the adjacent piece, that's the a over 2, and divide it by r. And that has the two variables that change. And of course, I'd like to get rid of the r and replace it with a theta. So I'm looking for something that relates theta or r to theta without having an x in it. And that's why the cosine function is perfect for that. If I did the sine function, that would be x over r. And then if I, solve this for r and put it into here, then I've got an x floating around. So I don't want to do that. And of course, tangent theta is the same thing. You would have x over a over 2. But again, that doesn't even have the r in it, so that's definitely not a good choice. Anyways, this is a good choice to go right there. And I'll do that one. So I'll leave the dx alone here, and here's cosine theta. But if you imagine solving this for r, you would then get, let's see, move the r over to here, you would get your a over 2 divided by cosine theta. And so if you square it, you're going to get an a over 2 squared, and then this would flip, and so you'd get a cosine squared. And so now this is cosine cubed. And this is something that doesn't change. So let me bring that out in front here. Okay, so at this point, what do I have? So I've got a 2k lambda, and I'll bring this a over 2 squared out in front. I got a dx, and I got a cosine cubed theta. All right, so good news here is I was able to get rid of one of the changing parameters, the r, and get it listed in terms of where I'm headed, which is a theta and a constant, and so I can pull the constant out. All right, so now let's play the same trick here. How can I relate x to theta? And I think we touched on that right here with the tangent. So tangent of theta is equal to x over a over 2. So we better come back to the picture, but here's theta, and so the opposite is the x, and the adjacent is the a over 2. And so I picked, again, the tangent one because that's the one that has the x and the theta in it without introducing an r or anything. Okay. In fact, why don't I just write the a over 2 together with the tangent theta is then equal to the x. Because now I can take the differential because I want a dx. And so when I take this differential, I get this a over 2. But the derivative of a tangent is a secant squared. Ooh. See, and then that's where I'm looking at this going, okay, I probably overdid it for this class. I didn't mean to pick one that was so hard. It's kind of it looks straightforward in terms of physics, but, seeing these calculus and the trig functions, this is where I'm not sure how high your calculus 130 went. I mean, we would do a lot of this in the more advanced calculus 150. But for you guys in the 130, I'm not sure how many trig identities you did. In either case, like I said, this is just a doozy of a problem. But anyways, you might have forgotten about the derivative or even how to switch the variables. Okay, so this is the secant squared. So let me put that in here. So this is 2k lambda a over 2 squared integral. Maybe I'll write the cosine cubed first, and now I can put my dx. So this is a over 2 times secant squared theta. Yay! All right, so now I got all thetas. In fact, this a over 2 is a constant. It can be brought out in front and cancel with one of those. And so you would have 2k lambda over a over 2. Okay, looking good. And, surprise, surprise, remember what a secant is. A secant is 1 over cosine. So a secant squared would be 1 over a cosine squared. And that's then going to be a cosine squared in the denominator is going to cancel with 2 of those. So you just end up with cosine. Oh, and I guess I'm sorry, when I did my little differential here, I forgot to put a d theta. And so there should be a d theta here and a d theta here. Okay, so I can't have a differential on one side without the other. So I took the differential of this side, dx, and then I would have the derivative of the tangent and then the d theta. Okay, now, wow. This is why I said, if you've done these before, you know now why we back here, we look at these variables and we go, okay, which is the best one to do? Is it best to change everything into an x or everything into a theta or everything into an r? And so with some experience, you begin to see that it's best to do a theta for something like this, and this is why. It actually just fell down into one of what we call our trig substitutions for our calculus here. All right. So, again, not being real sure how much you guys did calculus with trig functions, but I know you took derivatives, and so like the derivative of a sine is a cosine, so the reverse is true. The integral of a cosine is a sine. So that's what I get when I do my integral. Now, of course, we also should ask what are our limits. Now, let's go back to our picture. Remember, we're doing this half of the rod. And so as you think about this angle here and the first chunk of charge being right here, there would be 0 angle. So our limits would be 0. And then eventually we would get all the way over to here, which is, maybe I'll just call it theta maximum. The maximum angle you get as you get to the end of the rod. So I'll call it theta maximum. Because when we put in our limits, 0 to theta maximum, we then will have just sine of theta maximum, because then we would go minus sine of 0, which is 0. So maybe for completeness, I'll put sine of the maximum minus 0. Okay. Now, we can actually then come over here and actually look at the sine of this thing. So here it is. The sine would be the opposite over the hypotenuse. And the opposite is L over 2. That's how long that is. And the R, we can use Pythagorean's theorem. And so that would be L over 2 quantity squared plus A over 2 quantity squared square root. Nice. And let's see what I've got going on so far. I guess I could cancel off these two, and I'd have Coulomb constant times the lambda times the L. I guess I could flip that back up, so that's a 2 and an A. Let's see, did I get everything here? And so then this is an L squared over 4 plus an A squared over 4. Now, this 4 can be factored forward, and then we would have 1/4, and then we can square root it by itself, so we would get 1/2. So I'm going to put a 1/2 and then cancel that off. And then this can flip over, and so this is a 4 times a Coulomb's constant times a lambda times an L over A all over the square root of L squared plus A squared. Whew. Okay, well, if you're still hanging with me now, I think we are finally there, because I can do, I guess, one more step for K, and in place of lambda, I can put Q over L. And then, of course, it's multiplied by L, and then all of this is A over the square root of L squared plus A squared. And so the L's cancel off. And so finally we get 4KQ over, and then we got an A. And then we've got an L squared and an A squared. Yay! All right, but if you hung with me this long, good for you. But way beyond the scope and the amount of work that I intended or that's required for this class. Take care.